So I'm going to be talking about some work that I did while at the Malaria Atlas project before I joined Imperial. So there's quite a lot of topical overlap with Rohan's talk, which is good. It means it's easier for me to explain things. And I think I've presented some of this work at some of the other departmental seminars, so hopefully it's not sort of too dull, but I'm going to focus on sort of a different side of it this time, so perhaps it'll be hopefully still interesting anyway. So the topic is using auxiliary data sets for dimensionality reduction. So the Malaria Atlas project as a whole, sort of the aim is to be estimating spatial sort of malaria incidence and spatial malaria prevalence, often on a global scale. So here's an example of that. And so we sort of just continually developing methods that improve our ability to do that. So the kind of the starting point for this work is not looking globally anymore, but looking at individual countries and using incidence data that's from polygons, so sort of aerial data, sometimes relatively small area, but mostly sort of medium-sized area data. In quite a few of these slides, I use the acronym API, which is Annual Parasite Index. It's just rate per 1,000 people, which kind of puts things in the range of 0 to 100 or so, rather than often looking at sort of 0.001 incidences per person. And so we have started developing, we've been using these methods called disaggregation regression, where we're using polygon data to make predictions at a high resolution. And so I'm not going to talk too much about the details of how that works, but so that's kind of our baseline model, is this disaggregation regression. So in the work that follows, I'll be using two cross-validation schemes. On the left, a random cross-validation scheme, and on the right, a very spatial cross-validation scheme. So in particular, because the statistical models we use typically have a Gaussian random field to represent some spatial information, this spatial cross-validation scheme can tell you how well your predictions will be far from data, or perhaps in a neighboring country to where you have data. So it can be quite informative. So we unfortunately don't really have any data to validate our predictions at the pixel level, which is really the main task of the modeling exercise, is to predict at this sort of high resolution pixel level, but we don't have that data. So in the work that follows, this cross-validation is on the polygon level data on these kind of shapes. But if you're interested in a bit more sort of why we don't think that's a terrible idea, you can look at Rohan's recent paper where we use simulations to then kind of go back and actually say whether we did a good job at predicting the pixel level incidence. So this is our baseline and the 4 countries we're using in this study: Colombia, Indonesia, Madagascar, and Senegal. So this is a disaggregation regression model with I think this is the spatial cross-validation. We've got observed API along the x-axis and our predicted API along the y-axis. We sometimes do okay and sometimes do fairly terribly. These numbers here are correlations between the observed and predicted. That's our main performance metric. And the question is, can we improve on this? So I can't see a clock anywhere, so I have no idea how long I'm talking for. Okay, so in some of these countries, we've got these shapes, this polygon incidence data, but we also have the data that Rohan was focused on using, which is these prevalence surveys in very small areas. So these will be in either a village or perhaps one sort of one area in an urban area. And so in some countries, there's quite a lot of this data. For example, here in Madagascar, we've got a lot of these prevalence surveys. And so the question is, can we use these data to improve our predictions? So there's a couple of ways you can think about this. So we definitely want to use these data together. That's kind of the idea here. And so as Rohan was explaining as well, we have potentially lots of covariates and not lots of data. In a lot of countries, the area data is either tens or hundreds of data points at the polygon level. So it's not much data to be learning information about, tens or more of covariates. So one way we might think about doing this is using our prevalence data to do dimensionality reduction, but in a supervised way. So instead of doing PCA on our environmental covariates, for example, we can just say, well, why don't we use that prevalence data to guide that process and find really kind of informative combinations of those environmental covariates that help us predict prevalence. And if they predict prevalence, they're probably going to predict incidence as well. So in practice, what that means is we're fitting machine learning models to prevalence data, making predictions across the whole country and using those predictions as a new covariate. But another way you can frame this, instead of thinking about it in terms of dimensionality reduction, you can also think of it as model averaging or model stacking. So random forests, for example, the way they work is you fit lots of models, so hundreds of trees, and you average the predictions from these models, and that reduces variance without necessarily increasing your bias all that much. So instead of just purely averaging a lot of models, you can do what's called stacking, where you fit a number of models and then use a meta model to sort of weight how you should average those different models you fitted in the first place. And stacking has been shown to work well for predicting malaria prevalence in the past. But instead of using the malaria prevalence as both the base models and the meta model, perhaps instead we could use prevalence data as the base models, but then use our disaggregation regression on incidence as the meta model. So, and one way to think about this is, particularly in this disaggregation regression setting, that there's virtually no pre-built packages that handle this data in the way we'd want it to. So to use any machine learning algorithms is quite difficult. So instead, we can use machine learning on prevalence data and then kind of hopefully port those learned relationships across to the incidence setting. So the way that works is, so this top schematic is our baseline model. So we have our polygon incidence data, some environmental covariates, and they are combined in a disaggregation regression model. What we might do instead is use prevalence data from that country and combine that with environmental covariates and use machine learning models, fit machine learning models to those data, make predictions from those models across the whole study area, and that gives us our new covariates, which are these machine learning predictions, and then combine them with incidence data and again go into the disaggregation regression. So we call that here ML little l for ML local, and I'll go a bit into some slightly different schemes later if I have time. How are we doing? So it's a horrible picture, sorry about that, but these are five machine learning models we fitted to the prevalence data. So I think it's an elastic net model, can't remember the order now, maybe PPR, probably random forest, boosted regression trees, and a neural net model here. And what we can see is that there are some similarities in these predictions. So the scales are all different because that's how R plotted it. Sorry about that. But this sort of highland area in the middle is typically low relative to the other areas. But other than that, some of the fine-grained patterning is quite different. So we can think about, well, perhaps if we average over these models, we'll perhaps reduce our variance instead of sort of accidentally predicting an area very high. We're kind of finding consensus amongst models. So just to sort of clarify how this works in terms of cross-validation, we've got our outer cross-validation scheme, which is on the incidence data, on the polygon incidence data. But then sort of inside that, within each model using prevalence data, we do k-fold cross-validation to select the hyperparameters. So this is two examples of choosing the hyperparameters from elastic nets from two different countries. So towards the right, I think, is lasso. Towards the left is ridge regression. The colors, which are horribly plotted, are sort of the strength of the penalty. But you can see we have sort of quite interestingly different hyperparameters selected across countries, which is perhaps interesting. So then we take the best hyperparameter for each model in each case and take that forward, make predictions using that model, and that gives us our new covariates. And that gives us results that look like this. So on this left column here, we have our baseline as before. In the middle, we have a disaggregation regression model that's fitted to the environmental covariates and the machine learning predictions. And then on the right, we have models that are fitted to just the machine learning predictions. And in most cases, we get some improvement. So Colombia, we definitely get some marked improvement. Indonesia, we don't see any improvement. Madagascar, we see improvement, and Senegal, we don't see improvement. So, you know, maybe there's some benefits to this method. It's not probably world-changing. And so just to sort of discuss about what we're hoping to find when we stack models in this way is that we want uncorrelated models. So this is a correlation matrix. On this top corner, we've got all the environmental covariates. You can see there's some strong positive and negative correlations in there. Then this next set are machine learning models fitted to a global data set of prevalence data. And then on the next section of covariates are these predictions from just the data in one country. So we can see there's quite a lot of correlation between in each case, all the models that are fitted to the same prevalence data set have quite strong positive correlation, which is sort of not surprising. They're all trying to do the same thing. But for stacking to be effective, what we want is quite good models that are all quite uncorrelated. So these are all the global data set machine learning models. But for example, we can see that the models fitted to the global data set are much less correlated with the models fitted to the Madagascar only data set. So perhaps we can combine predictions from both of these sets of models to improve our model performance further. But we found that actually that didn't improve our models at all, really. So here we've got, again, our baseline, just the environmental covariates. Here we've got the models that use the predictions from just the machine learning models fitted to the global data set. And here we've got the models fitted to the local and the global data set. And sometimes these models are better than the baseline, but they're never better than just the MLL models, which surprised me quite a lot and was a bit of a shame, but well. So to start wrapping up, we've sort of taken some of these ideas and applied them at global scales, both to Plasmodium vivax and Plasmodium falciparum. I should learn how to say that word. And happy to take any questions. Thank you very much.